Hello, BC Calculus students. This is Mr. Johnson, and this is section 6.4, which is on arc length. So what we're going to talk about is basically a curve in space that would either be defined in Cartesian coordinates, so x and y, or defined, I guess, more often in parametric coordinates. So the parametric coordinates are going to be the ones where we're looking at f of t, so x is a function of f of t, or y is a function of g of t. And we're looking at a curve in space and just kind of in general. So let's just say you have maybe a point here and a point here. Let's maybe draw in, this might help a little bit. So draw in a coordinate axes. So maybe looks like this. Here's y and x. And maybe this point is A and this point might be B. And so the idea here is that we're trying to figure out what the length of this curve is. You know, we're not going a straight distance, a straight shot at it, linear distance. We're looking at this kind of curved distance. So we call that arc length. So how we analyze this is a lot like how we've done a lot of our integration, which is where we kind of break it down into smaller pieces. And this is not at all a formal proof. This is simply just a quick explanation of what we're kind of trying to do here. So if you were to zoom in on this curve, and maybe we pick a point, I'll put it in blue. So we pick a point like right here, and let's pretend like we really zoom in and we come up with what's almost a straight little like a line or a little section of it that's really straight, almost like a line along that particular curve. And if we were to analyze that, let's call this arc length is often defined as S. So let's call this little change ds, okay? So the change in S, and we want to think about this along the entire curve. So maybe we pick one there, and then we pick another one, there, and then we pick another one here, and I don't really have that many colors here, and we pick another one there, and so on. So we basically come up with these tiny little line segments that we are analyzing along the curve. Well, essentially, we could set up an infinite number of those, just like we would rectangles for the area underneath a curve, or maybe for the volume of revolution, we come up with all of these volumes of disks or washers, that kind of thing. You know how we take integrals and we integrate over a region which simulates multiple of that item. So in this case, it would be a multiple segments that we would be adding up. So we could say that we would add up this goofy change in S, excuse me, the arc length. Now, in terms of variables, that doesn't make a whole lot of sense because we're used to x's and y's and maybe the occasional t when it's in parametric form. So we have to think about what does that sort of symbolize based on the variables that we're used to. So let's go back to this little segment. I'm going to make it a little bit bigger. Okay, so I'm going to just kind of draw in. Let's just pretend like that is our small line segment along the curve. If that's ds, well, if we're thinking about change at this particular moment, and again, we're so zoomed in that it's just very minor change, but I'm kind of making it look bigger so we can draw it in. This would be my change in x, and this would be my change in y. So those two items would be how I would describe my horizontal and vertical change. So you can see that based on our differentials, we're trying to sort of calculate the hypotenuse of this little triangle. So if we were to think of this as simply just dx squared plus dy squared, it would give us ds squared. And of course, back to our integral, we want to integrate ds. So therefore, we're going to solve for ds, which is the square root of dx squared plus dy squared. Okay, so this is a little bit better because we are dealing with more standard differentials, but really we're still in a little bit of trouble because all of a sudden we have two different differentials that have different variables. So how do we address the fact that we have this dx and this dy? So what we're going to do is factor out a dx. So it looks like this. We have the square root of, and I'm going to factor out a dx squared, which means that I have 1 plus dy squared divided by dx squared. I'm going to rewrite that again a little bit because it's kind of messy right now. If you take the square root, since it's factored out now, if you take the square root of dx squared, you get dx. I'm going to obviously put that on the right side because that's what we're used to. So I have 1 plus, I'm going to write this as dy dx squared, and then my dx that I factored out from right here comes out of the radical, and we're just going to put on that side. And this is a much more standard form because remember, we have now a arc length formula that is represented based on the derivative of a function with respect to x. Now, there are kind of three different ways that we're going to represent this. One of the ways will obviously be in terms of x, the other way will be in terms of y, and then we will also have the parametric form. So I'm not going to get in this video, I'm not going to really get into super in depth as to how each of the forms is connected right now, but it's really all in a very similar way to what you've seen so far. So this would be of some sort of equation of the form y equals f of x, where you have some sort of y equal to a Cartesian equation where it's just in terms of x. That's what we're dealing with in this regard. Below, you will see that there is an arc length formula in parametric form. This is probably more common, and we could get there if we were to kind of wiggle around our values, which I can show you at a different time. But you want to memorize this one. So really, in our list here, we have, and I will specify this on the next page, but this is going to be parametric form. And if you'd like, and again, it's on the next page, but if you'd like, you can write down the arc length, which is L. You could call it S. It has all sorts of different variables that we could use. This one is if you have, oops, that's not right, sorry. If you have an equation in the form y equals f of x, or g of x, or something like that. And then the third one you need to know is the arc length. It's really similar actually, but it's going to be dx dy. This one's not, this is probably the most rare one because this is in terms of y. So it would be like stuff in the form x equal to g of y or something kind of bizarre like that. Okay, so let's take a look at example 1. This is obviously in parametric form. And so we have x equal to t squared, y equal to t cubed. The curve lies between the points 1, 1 and 4, 8. So if you were to think about this graphically, so this is x and y, and you have 1, 1, and then 4, 8. I'll kind of exaggerate it a little bit. So maybe it looks like this. We're just looking for the curve between, or the arc length between these 2 points. Now, one of the things that we have to always make sure, this is true with parametric equations all the time, is that we analyze the correct variable. So in this case, we're looking at t, which we're given points that are in x and y. So if we have x equal to 1 and y equal to 1, and then x equal to 4, and then y equal to 8, we have to think about what is the t value associated with those points. So if you were to take and put 1 in right here and 1 in right there, sorry, other way around. If you were to put 1 in for x and 1 in for y, t would be clearly 1. So this point corresponds with t equal to 1. And then if you were to put x equal to, so x equal to 4 and y equal to 8, then t would very clearly be 2. So that's what we have to use for our integration, okay? So t is 2 for this one. All right, our integral then will be from 1 to 2, and we're going to use the formula above. So it's the square root of dx dt squared plus dy dt squared, which we're going to go ahead and calculate right now. And it's with respect to t. Okay, so again, we have our original. We have x equal to t squared. So x prime is the same thing as dx dt, and that will be 2t. And then y prime is the same thing as dy dt, and that is going to be 3t squared. Okay, here is our integral. So the integral from 1 to 2 of the square root of 2t squared plus 3t squared, oops, and then dt. And we could, clearly simplify this. We could also analyze this. I'm not going to get into that analysis right now just because I want to make sure we try some problems here. And I'm trying to make this a little bit on the shorter side. So this would be our integral that would represent that arc length. And again, without a calculator or with a calculator, we might have to analyze something like that. And we'll get to that later. Here's the next page. Okay, I mentioned there are the other formulas. Here they are. You can refer back to the other page and make a couple notes if you'd like, but this one would be with respect to x, and this is with respect to y. And so let's go ahead and try one. So for example, if you take this hyperbola xy equal to 1, let's say that we want to start and think about this as y equal to 1 over x. So we have our points 1, 1 to 2, 1/2. The derivative here is obviously dy dx. That's going to be -1 over x squared. So the integral will be from 1 to 2, and it will be the square root of 1 plus this guy squared dx. Okay, so that would be something we could type into the calculator if we wanted to. Now let's say that you decided to solve for x. Okay, and we have x prime, which is the same thing as dx dy. This is less natural for us, I think. And the integral then would go from 1 to 1/2. It's the y values now. Obviously, that's kind of backwards, right? We want to go from 1/2 to 1, but we can negate that. But keep in mind that it is from here to this point. So we want to just follow the form there. We have our square root of 1 plus -1 over y squared dy. So if you were to use your calculator and test both of these, keep in mind that your calculator only knows the variable x. So you'd have to use x for both variables. But if you type those in, you're going to get identical definite integrals. Let's move on to example 3. So it says, which of the following gives the length of the curve? So that's the same thing. This little statement right here is the same thing as arc length, okay? All right, defined by the parametric equations, x of t and y of t from 0 to 1. So they're actually giving us a lot of useful stuff. We already know those limits there. We do want to figure out x prime, which is t, and we also want to figure out y prime, which is t squared. They're giving us really easy functions to work with here. So it's the square root of x of t, that's just t squared, and y prime of t, which is t squared. Okay, that's squared, and then dt. So we have, as a final answer, letter D. Okay, let's go ahead and move on to the last page. All right, now this is actually not arc length. This is going to be the tangent line for parametric equations. And so the reason that this is in here and the reason that we have additional information down here is that we pulled from section 3.4, which is on parametric equations and vectors. And this kind of is connected to that topic. So we don't really do this, the analysis of arc length until now because it fits into chapter 6. But technically it all kind of goes together. So often what you'll find is when you're doing a parametric equation, like a FRQ question, you might see arc length show up. Other times it's just really separated, but it is connected a lot of times to the study of parametrics because of the form that it's in. So this is just a quick review of that. Remember, for a tangent line, you do need a slope. You can see, let's see, where is it here? There we go. Sorry, it took me a second to find it. So here's your slope. That's the slope of a parametric equation. So we have dy dx is our common slope notation, but it's going to be dy dt divided by dx dt. So for our particular example, dy dt will be 3t squared plus 5, and dx dt will be just simply 2t. T is 1, so let's go ahead and evaluate this at 1. So we have 8 divided by 2, so that's going to give us 4. That's going to be our slope, okay? We also want to find our x value and our y value. So x of 1 is 3 plus 1 squared, so that's 4, and y of 1 will be 1 plus 5, so that's going to be 6. So your equation in point slope form is y minus 6 equal to 4 times x minus 4. Looks like they don't want that form, so we're going to just move this over. This is going to be y equals 4x minus 16 plus 6. And so we end up getting option B for this. Okay, that does it for arc length. There's other ones that we will practice. There's examples here in our notes. But for right now, that's the overview. Just remember those three formulas. Thanks.